the bus and stuff.
Yeah, okay. So Rudy Peterson is going to talk about P4Cub, a little language for big routers.
Hello, everybody. As you may have heard, my name is Rudy Peterson. And today, I am a post-undergraduate researcher. I know that sounds weird. And today I'll be presenting the work that my collaborators and I at Cornell have been developing about an IR for networks. So different languages have different users and different audiences. For example, the surface syntax needs to be readable and writable for programmers. You know, it's nice to have some syntactic sugar here. That can be pretty good. But on the other hand, intermediate languages should be designed with compiler writers in mind, and what representation is good for transformations, program analyses, and so on. Finally, target languages should be designed with hardware in mind and need to be able to perform and represent computations quickly and correctly. Now, I'm going to talk about what we as proof engineers like to see in IR design. We want to isolate a handful of features to change from IR to IR, enabling relatively straightforward proofs about each transformation. CompCert is a great example of this. Each IR serves a purpose, has particular properties that make it geared towards writing specific transformations and analyses, and then proving theorems about them. Furthermore, the IRs on CompCert are flexible enough to target various hardware, such as that for PowerPC, x86, and so on. So we would like to apply this kind of design to the networking domain. However, networks include hardware beyond just general CPUs. They include programmable NICs, FPGAs, switch pipelines, and all other kinds of alphabet soup, you know. So we can't solely rely on CompCert, and we need to engineer verify compilers for these targets. And many of these architectures can be programmed in P4. P4 is a network language used to write packet processing programs. P4 fundamentally is great because of its flexibility, is statically allocated, and all programs halt. I know, pretty good, right? So thus P4 seems like an ideal choice to build a verify compiler for a networking language. So there's already a plethora of great work on formalizing P4. In Petra, we built a compiler front end, a type checker, an interpreter, and OCaml. The folks at KTH have developed whole for P4, an embedding of P4's surface semantics in whole for. Lastly, our collaborators at Princeton are implementing P4 Lite, a high-level IR and program logic for P4 in Coq. All of these do a good job of providing formal foundations for P4's surface language. Because all of these systems target the surface language or something close, there is room in the design space for an IR that's good for verification rather than for humans to reason about. So when you see these red check marks and green check marks here, I'm not saying that one is the devil and the other is heavenly or whatever. It's just from my point of view as a proof engineer, and you might disagree, but I'm on the podium, so. But anyway, yeah, so as proof engineers, we need mechanized semantics. There's no way around that. And whole for P4 and P4 Lite do just that. And here's some more specific criteria for a good mechanized IR. Whole for P4 and P4 Lite have heapless semantics. A heapless semantics is good for proofs in meta theory. In Petra, we chose to do something like OCaml refs, which, while was a good choice for an understandable pen and paper formalization, is unnecessary because P4 is statically allocated anyway, and this would require more machinery and mechanized proofs. P4 Lite, like C Lite, has side effects hoisted out of expressions. Side effects and expressions can be tricky to reason about, so it's nice to have things like function calls at the statement level. Now, one thing about all of these systems is that they have mutual induction. And while this is a fine choice to make for the surface syntax and semantics, I find it better to avoid unwieldy lemmas and induction schemes when possible. Lastly, all of these systems use name variables. While name variables are great for humans to read and write in programs, doing proofs about strings and free variables can be cumbersome. I'm sure many of us have experiences of doing a proof of strings and it unwinds it to the entire like car constructor thing. And, But anyway, so with all of this in mind, we built P4Cub. We mechanized the semantics in Coq. There's no heap, expressions are pure, no mutual induction, and we adopted a nameless representation. So P4Cub is the next step in compilation after P4 Lite. It reduces P4 to a core set of orthogonal features, and it has better control over variable binding and side effects than prior art. We have put it to work in several case studies, including verify compiler passes. So now to talk about P4Cub design. Let's jump into a running example. Here we have a snippet of a surface level P4 program. The program includes a table, which is P4's construct for network hardware's match action table. Here the table checks that if the destination address in an Ethernet header and then decides either to forward the packet or drop it. Note that I need to mention that table semantics are determined by the control plane, and P4 is a data plane programming language, meaning that whether or not the packet is dropped, forwarded, whatever, it's beyond the programmer's control. And this is a feature specific to networks. Below the table, we have a switch statement. In the switch statement, the table is applied, and the result of the computation is checked. If action run is forward, then the packet is forwarded. If it's dropped, it's dropped. The snippet includes a table which we want P4Cub to have in order for it to represent network programming. However, it features a table application within an expression, which may be stateful and therefore nasty to reason about. It also has a switch statement and enums, which may be compiled away. So here's the same program in P4Cub. Tables are still in P4Cub because they're important to networking. But we've hoisted the table application to the statement level, isolating any side effects. We also compiled the switch to a conditional and the enums to unsigned integers. Well, enums and switch statements are nice features for a programmer. They're unnecessary for a compiler IR. Now, let's take a look at P4 data types. P4 has structs, headers, and arrays. Headers are like structs, but are distinguished by a validity bit and play an important role in network programming. Arrays have a type for an empty array, and that's why all of these have different data in them and why they're different constructors. But while these are all semantically distinct, writing the expression data type like this will lead to multiple sub-goals where you have to prove something about a list of expressions. And I contend that this is not ideal, and we should collapse these into one constructor while still being able to distinguish them. Our solution was to write a variant with the data particular to each construct. Then, in the expression data type, we use that as a flag. Now, in induction proofs, we only have one goal with a list of expressions, making proofs much less cumbersome and more intuitive. We've applied this principle to other areas of our design as well. Now here's all of P4Cub's syntax. The point being that it fits on one slide, which may not sound like the best thing, like, oh, Rudy, all of lambda calculus fits on one slide. Yeah, I know. But the thing to note here is that the grammar for P4 syntax, the surface language, with all of its bells and whistles, does not. In fact, you can look at the appendix for the language specification, and you can keep scrolling and eat popcorn while you're doing it, or start cooking popcorn. You know, it might take a while. So now I'd like to talk about how we have used P4Cub. All of this is ongoing work where we're writing verify compiler passes, mechanized type soundness proofs, and an automated program verifier. So let's start with the verify compilation. So we've been developing a pass to lift certain problematic expressions. These expressions may have side effects or other interesting behavior in P4 that we would like to isolate at the statement level. But to be clear, P4Cub itself does not have side effects and expressions. It's just that some P4 features, such as arbitrary fixed width bit strings, like you could have bit 32, but you could also have like bit 42, bit 100, bit 9001, whatever. These might prove problematic in later IRs, and we would like to lift these terms out. For instance, say that E1 is such a troublesome term and needs to be lifted in this program. We would like to produce a program that factors out E1 where this new variable x is initialized with E1. And this seems pretty straightforward at first. However, what if x was already free in the program? Like, what if E2 was x? Then generating a non-fresh name could break the correctness of lifting. So, as usual, we need to pay attention to free and bound variables, fresh names, etc. This is particularly true for us, since we are doing the proof in Coq. Now, here is our first stab at trying to prove a pass correct for expressions. P4Cub initially did have named variables. And there's a lot in here to unpack. Most of it has to do with fresh name generation. This proof was, in fact, what motivated us to switch to a nameless representation. And I'll explain why. So here we need to make sure that any names generated, which is the gen variable, don't collide with those in epsilon, the store for values. In short, this limit states that you're going to know that E evaluates to a value V, and that the names in the store epsilon are restricted by some fresh name generator. And that lifting E, using the generator, produces a statement S with a sequence of the lifted expressions declared, a new lifted expression E prime, and a new fresh name generator, gen prime. And then there exists some store epsilon prime such that S evaluates to epsilon prime. And that the lifted expression evaluates to the same value under epsilon prime. And that the bindings in epsilon are a subset of those in epsilon prime. And that the domain of epsilon prime is restricted by a new fresh name generator. Yeah, that was a run-on sentence, my bad. But anyway, so trying to state and prove something like this was frustrating. And the source of this frustration was, at the time, our representation used name variables. So what if instead we went to de Bruijn variables for an imperative language? Yes. So this theorem statement is much more elegant than the last. It's much shorter, and let's get into it. So here we start by evaluating E again, but this time the value store, instead of being a map, is a list of values. Then we lift E to get a lifted expression E prime, not needing a fresh name generator here. And here we also get a sequence of lifted terms E's. So then there exists some list of values V's such that if we evaluate the E's as a sequence of declarations, we get the V's, and then we evaluate the lifted expression E prime, appending the values as a prefix to the environment to get the same V. Now here we were actually able to do proofs about expressions for this, and are confident we will be able to complete proofs or statements as well. We've also used P4Cub to carry out mechanized proofs of type soundness. So we've proven type soundness for expressions, and these preservation and progress statements are pretty standard. What's interesting is that epsilon is a list of values, and gamma is a list of types. So values at certain de Bruijn indices type as the corresponding type in gamma. Lastly, we used P4Cub to implement an automated program verifier. So we've developed a backend that translates programs into Dijkstra's guarded command line language, or GCL. In an unverified path, P4Cub is compiled to GCL, and then SMTlib generates verification conditions, and Z3 tries to solve them. Our group attempted to write a similar system, P4V, published at SIGCOMM 18, by the way, and that took over a year. However, this effort only took 3 months because it leveraged P4Cub's design. So in summary, P4Cub is a simple IR for P4. It supports domain-specific reasoning for packet processing programs, and the cock formalization is ergonomic and has been put to good use. We would like to complete a verified compiler to C by harnessing COMSOR's properties. We would also like to complete a verified compiler for network hardware as well. We would like to design more lower-level IRs and extend P4Cub's meta theory. So thank you all so much for listening. Feel free to check out our work on GitHub and find bugs in it, whatever. And I am happy to take any questions.
Thanks a lot. We have the treat of having a speaker finish early, so there's plenty of time for questions.
You said you don't like nested and mutual induction because then you need to define induction schemes and all that stuff. But then your definition does have nested induction, and Coq also does not generate good induction schemes for that by default. So why is nested induction okay, but mutual induction not?
That is an excellent question. So this is totally my opinion, so you may feel free to disagree. But that was something that we were considering in our design, was like, for these things with lists of expressions. I can even go back to that slide. Where we were like, sorry, so many slides. Okay. So yeah, like we could have done this as like having like a nil constructor or a con constructor like inside of the expression thing, or we could have like mutually defined a list data type or a list like data type with this. But for something like this, we wanted to make sure we could only form like well-formed expressions with this. Like we couldn't make something where like we were consing something that you can't con something onto. And at the same time, we wanted to take advantage of like Coq's list library and all of that machinery there. But that's a good question. Yeah.
But so now you still need to define your own induction scheme.
Oh yeah, we did. But honestly, that wasn't as bad. And I will say that, not to throw stones, but in like in other experiences, like I've seen both of that, where like there was mutual induction, but there was also like you had to find an induction principle for that. And I feel it's like that's like in the quarter, like the square, the worst one. But you know, but thank you.
The P4 light formalization, I think, that's what you described, where it's like a list like data set. So the P4 light formalization, I think, doesn't use nested inductives. It uses mutual induction to represent lists inside of lists of expressions, I think.
I think it does both.
It does both.
I think it does some,
and,
like, because there's...
Our experience working on that was that the induction schemes for that were harder to work with and harder to maintain than
Yeah.
no, doing it. I don't know. It's a little subjective, but anyway.
I mean, I enjoy like learning about all the cool cock features as much as anybody else, but induction schemes can be fun once in a while, but you know, maybe not for a big development.
Other questions?
Can you expand a little bit on the kind of meta-theorem that you want to prove about the language? I don't know nothing about P4, so.
Oh,
Do you have some interesting property that you want to target, or?
Oh, sorry, could you say that again?
Do you have special properties that you want to study about the language?
Yeah, that's a good question. So, P4 programs are all terminating, but this isn't like something that's easy to prove about it, especially because it has like these packet parsers, which are basically state machines. And P4 itself has rules about how they can't loop on forever, but it would be like very non-trivial to prove in cock. So we are working with another team at Cornell with doing that, and hopefully these two projects will intersect and we'll have some strong tools to be able to prove that about P4Cub. So thank you.
Thanks.
Other questions? Yes. Back.
Just a further answer to that question, I think one fruitful area could be doing resource analyses, or understanding both hardware costs and also performance characteristics of P4 programs, because the cost model for P4 is not written down carefully, but is intended to be there, and it'd be really nice to have that meta theory worked out.
I think we have time for another question. All right. Love to be early. Let's thank our speaker again.